My name is Felix Kornišev. I'm a researcher at the Maritime Museum. I am happy to welcome you from my part as well to today's Maritime Forum, or Mereforum as we say in Estonian. But without further ado, I would like to introduce our speaker, Richard Dunn, from the Science Museum London today, where he works as a keeper of technologies and engineering. He has previously worked as curator of history of navigation and then senior curator for the history of science at Royal Museums Greenwich or National Maritime Museum in London. During his career as a historian of science, he has touched upon various topics related to the history of navigation. I have a couple of books here with me that I will want to show you around. One of them I'm just going to show you is Finding Longitude, together with Rebecca Higit, who is also present. Also, we have many experts of navigation here today, so please, here. Then we have this kind of book called Navigational Enterprises in Europe and its Empires, also together with Rebecca Higit, and it includes articles by presenters of this conference as well, so please. But please return them later. And the latest book called The Board of Longitude, which is more specific and concentrates on the British side of the longitude story. I actually had two more, but I couldn't get hold of them today. But anyway, Richard's talk today is called There and Back Again, how navigation at sea did and didn't change after the longitude problem was solved. In his talk, he will look at how the methods of fixing a ship's east-west position developed during the 18th century, drawing on examples from a range of voyages, trading, exploratory and naval, from the early 18th century to the 19th century. I'm sure it will serve as a fascinating insight to what really happened at sea, from routine and successful navigation to mishap and disaster. So please, Richard, the floor is yours.
Thank you. Thank you very much. So firstly, thank you for the invitation to speak here. So it's a great honour. It's lovely to be back. I came to Tallinn very briefly 10 years or so ago. It's lovely to be back again. Apologies, I will speak in English. Maybe not. That may not be a problem. Shouldn't be a problem for most of you. So this talk is the result of thinking about innovation in navigation in the 18th century, notably the successful development of practical methods for finding a ship's longitude, its east-west position at sea. And the question that's kind of taxed me for years is how and when this actually changed what seafarers did on ships. How quickly did they adopt new methods? Did they adopt new methods? Why and when? Now, I should note that the research is very much based on British navigation, but I will try and touch on one or two examples from this part of Europe, although this might be of ships coming to the Baltic rather than about Baltic seafarers. Now, let's try that one. The critical change in navigation I'm going to examine arises from the successful testing in the 1760s. It's also often told as primarily a British story, arising from an Act of Parliament in 1714 that offered life-changing sums of money to anyone who could devise a practical solution for finding a ship's east-west position at sea. And this created a group of commissioners of longitude who would judge and administer this scheme, and they later called the Board of Longitude. And key characters in this story are notably John Harrison, on your right, a clockmaker who successfully produced a sea watch that did work in those sea trials, and other figures such as Astronomer Royal Neville Maskelyne, who was probably the most important figure in the Board of Longitude through the later part of the Harrison story and actually beyond Harrison's time. But we should acknowledge that the story of the quest for longitude was a European one. In terms of national interest, Portugal, Spain, the Netherlands and France, all at different times offered rewards for the longitude problem. And it was European in terms of some of the individuals who had an impact on the development of new methods in the 1760s. So here on the left, Tobias Meyer, who's responsible for developing the theory of the moon's motion and tables of the moon's motion that allowed one method of finding longitude to be developed. And his work was in turn partly based on that of Leonhard Euler, who was Swiss-born but actually was at the Academy of Sciences in St. Petersburg. Both encouraged Meyer to submit his ideas to the British Commissioners of Longitude, and as I said, his theoretical work underpinned a lot of Meyer's. In the history of the board, there were also a number of individuals from, broadly speaking, this part of the world, who sent their ideas to the commissioners for consideration. Here, examples: Wolfgang Kraft, another an astronomer at the Academy of Sciences in St. Petersburg, and on the right, a scheme proposed by Christian Karl Laus, who was a professor at the Naval Academy in Copenhagen. Laus also is interesting for translating into Danish the description of John Harrison's Timekeeper within only a few months of it being published in England. And his edition of that work also included an account of the developments leading up to Harrison's design. So to come to the meat of my talk, I will focus today on, largely focus on successful, therefore in some senses uneventful navigation, rather more than shipwrecks, although these can teach us a lot, and I will discuss one briefly towards the end of the talk. And though based on English sources, what I say will be relevant beyond Britain in this period because of the trans-European nature of navigation through the movement of people and ideas. Ships often had crews from a number of countries, so were polyglot. And in particular for this region, through the link between Russia and Britain in naval and maritime matters. This had begun under Tsar Peter I, who created a substantial Baltic fleet centred on the new capital of St. Petersburg and turned into particular to Britain for maritime expertise. And this began a traffic of expertise and students between Britain and the Russian Navy through the 18th and into the 19th century. So how did people navigate before new methods of longitude finding came about? Navigation, safely getting a ship from A to B and hopefully back to A again, actually is about assembling lots of different bits of information. And the well-trained navigator in the mid-18th century had quite a number of tools and techniques to gather evidence about where the vessel was, which way it was heading, whether hazards or critical points of change in the voyage, turning points, were coming up, and indeed where its destination lay. And this information came from many sources. This illustration on the left shows a number of the instruments available. So I'll just stand and point. Instruments for determining the ship's speed, the log and line. Let's do that again. Yeah, okay. I won't touch the screen. Instruments such as the compass for showing the ship's heading, a leaden line to measure the depth, and then instruments for doing astronomical observations for latitude finding. I'll talk a little more about these in turn. But importantly, methods for recording those bits of data and so calculating the position. There were other aids. There were printed aids, so charts and books of sailing directions. These told you how to get between different places. So here I've picked a bit of the local area. So we're here. And part of a set of sailing directions to get to Tallinn Revel, as it's called there. So this, would tell you that you need to kind of sail below this island, then turn rightish. And until you get the city in view and tells you where to anchor. So it's local knowledge. And this is one form of navigation called pilotage, which is about very, very local and coastal waters. And there are other techniques which we call more oceanic navigation when you're out of sight of land. But these are all important bits of information. And the alert seamen watch for other clues too. Birds or seaweed might show the proximity of land. Particular birds with particular patterns of flight in, say, in the morning and evening might show you which direction land lay in. And obviously specific sea and landmarks would be things to look out for. As the famous British diarist Samuel Pepys noted, the best navigator is the best looker out. If in doubt, of course, ask a passerby. And that genuinely was a thing people did. They might pass a ship and ask them where they thought they were. Now, I'll come back to some of these in practice shortly. But firstly, let's do some spherical geometry. Very simple. Sorry, I will only say very simple things. Try to. So European navigators thought principally in terms of latitude and longitude as the means by which to plot a ship's position on the spherical surface of the Earth. So latitude is a measure of your angular position north or south of the equator, longitude of your position east and west. There are important things to notice. Lines of latitude are parallel, so as you head north or south, an angular change in latitude is always the same linear change in terms of nautical miles. Longitude lines meet at the poles, so actually the further north or the further south you get, the shorter the distance of, say, a degree of longitude is, going to zero at the poles. This will be important for the main method of navigation. Now, thinking about latitude, it's relatively easy to determine your latitude from, say, the sun, not shown to scale in this image. But imagine our seafarer here is just north of Britain. So this is his local horizon, and his latitude is this angle. So this is the angle at the Earth's centre, which determines his latitude. If he then observes the angle of the sun, so the observed angle is this angle above the horizon, the complement of that angle, so 90 minus his observed angle, is the same as the latitude angle. So that's more or less true. You have to do some other corrections that I'll touch on briefly later. So latitude is relatively easy to do. And by the mid-18th century, there were a number of instruments available for making those measurements. And the one that was becoming particularly popular by this time was the Hadley quadrant, or later known as the octant. So that's principally the instrument we'll be dealing with for the rest of this talk. Importantly, this was developed in the 1730s, initially in the context of finding longitude, but actually found its place much more in terms of latitude determination and also local time determination, which we'll come on to. Longitude I'll come back to, because at this point there wasn't a way of directly measuring it in the way that you can directly measure latitude in the mid-18th century. So this is an example of what's known as the day's work on a ship. This one happens to be by James Cook, but not when he's being an explorer. This is just before he becomes an explorer, as it were, when he's doing yearly trips across the Atlantic in order to do surveying work in Newfoundland. But it's a lovely, neat page of a kind of standard naval log here in the 1760s, but pre any longitude methods other than dead reckoning, which we'll come on to. So what you have is down the left, the hour of the day, so two sets of 12. Then you have the distance travelled of the ship each hour, measured on the hour, measured each hour with a log and line. This is essentially a bit of wood you throw out the back of the ship. You time it for about 30 seconds, and the amount of rope paid out gives you a measure of the ship's speed at that point. So that allows you to determine how far it travels in each hour. In the next column is the directions that the ship is heading each hour, or changes in direction, measured with a magnetic compass. And we also have in this log determination of the variation of the compass done for that day. So that's how much the compass, the difference between true north and magnetic north, which varies across the globe. Then we have at noon an observation for the latitude. I should have said you need to measure the angular height of the sun at its highest point, and that helps you determine your latitude. Then at the bottom, we have another set of numbers which are the results of calculations based on this information, which essentially are using your heading and distance travelled and the accumulated total of those to work out your change in position in terms of latitude here and longitude, or this is your final position based on the changes in position. That's not a straightforward bit of work going on here. But that is the principle of dead reckoning, is that you're basically going, I travelled this way, this way, this way. So if that was my starting position, this is my end position. This is the kind of calculation that lies behind this work. This is from a little later from a chap called Edward Ryu, who I'm going to mention a number of times because he really helpfully left a lot of his rough workings in notebooks done in the 1780s. On the left, we have the calculation for latitude. So you see, this is relatively simple, and what we have is the observation, 64.19, taken from 90 to give 24.41. A figure for the declination, that's how far north or south of the equator the sun is at that time of year, because it changes across the year, being at the equator at the equinox, and then at the furthest at the solstices. So those are added, and then there's a correction for the index error, basically a known regular error of reading on his octant. And that gives his final figure. So it's a fairly simple calculation. When we come to doing the other bits of work, the working out his latitude and longitude, this is the kind of calculations you do. And you see what you have down here are the headings and the distances travelled. These then have to be converted into north-south changes and east-west changes. One of the difficulties here then is that, as I said, the length of a degree of longitude varies according to latitude. So you have these incredible sets of tables which say that if you're at a latitude of, say, 40 degrees, and you go this many nautical miles, this is your change in longitude, or this is your change in distance if you're along a particular heading. So they're fascinating things to look at, not at all. But anyway, I'm not going to expect you to understand this. There's no test at the end. But this is just to show you that there's a lot of kind of arithmetic going on in dead reckoning. So dead reckoning is not in itself a simple thing. Now, I mentioned the log and line earlier because that's actually also an important navigational tool and can be helped, obviously, for safety reasons, checking you're not about to run aground, but also helping find your position close to coastlines. And you'll see as Cook in the same ship 3 years later is approaching England, there's several notes of having sounded, noting the depth, but also what has been brought up with the lead. So the lead would have on its bottom an indentation, and you would put some wax or tallow in there and pick up some of the seabed. And there were tables that would tell you if you were approaching a particular bit of coast, and the depth was a certain depth, and if it was, say, coarse ooze that you'd picked up, that would tell you roughly where you were. So it was a position fixing technique and could sometimes be used to correct people's position. There were also things said, for instance, some sailors said that you could tell the west from the east bits of the North Sea because with the western seabed material, you could crack that in your teeth, but not with the eastern seabed. I don't know what that tells us about the geology of the North Sea. Okay, so that's some of the techniques, and I've talked in particular about dead reckoning. Now, historical accounts typically make much of the problems of dead reckoning, but we should recognise that by the mid-18th century, mariners had been using it to sail the world's oceans for generations. This is a map from 1677 that picks out the kind of typical sea routes of seafarers from several countries, including France. So you can see they're sailing pretty much the whole world. So it does work. That said, it was known to have problems. Errors could accumulate over long voyages. If you're a long time out of sight of land, any errors are likely to mount up. And things like ocean currents could greatly affect your position and were almost impossible to measure from the ship because you're moving with the water. So it's very hard to measure a current and therefore assess the effect of that current. So there were conservative practices that allowed seafarers to compensate for some of these known problems. For instance, overestimating your distance run each day so that you would be looking out well ahead of time for land. But nevertheless, these problems did mean that seafarers and others understood that being able to measure longitude independently of dead reckoning in the same way that latitude could be measured independently of dead reckoning would be very valuable. And being able to measure latitude independently was also a way of providing some kind of check on your dead reckoning position. So let's do some more spherical geometry. Now, longitude is your east-west position. Because it's a measure in the direction of the Earth's rotation, we can think of the longitude difference between two places as the difference in their local times. So local time is the time that the sun gives you where you are. It rises at kind of 6 a.m. It's at the highest point in the sky at noon, for you locally. So if we imagine the sun is rising at 6 a.m. where I'm from, then if you're instead roughly here, I hope that's about right, the sun would have risen actually 99 minutes earlier. So it would be about 7:39 in the morning. Whereas if you were in the Indian Ocean, the sun might have risen 4 hours earlier. So you'd be 10 o'clock in the morning. So that's quite a straightforward principle. As long as you know the time at your ship, you get that from the sun, and you know the time somewhere else, and you know the position of that place, then you can work out the longitude difference with 1 hour of time equating to 15 degrees of longitude. Obviously, the problem is, how do you know the time somewhere else? And that's the thing that people had been grappling with for a long time for most longitude methods. There are other ways of doing it, but I'm not going to go into them. So the principle is straightforward. The practice is impossible. But it had long suggested a range of solutions, of which two emerged following the encouragement of the British Longitude Act of 1714 and were then tested at sea in the 1760s. So firstly, you could just have a timekeeper, a clock or a watch, set it to your reference time, take it with you on the ship, determine local time from the sun, compare the two, calculate your longitude. From the 1730s, John Harrison, had created sea clocks that did quite well, and then finally in the late 1750s with his son William, created the marine timekeeper or sea watch, we now call H4, that underwent successful trials in the 1760s. That's simplifying the story, but by this time, through the work of Tobias Meyer, who I showed you earlier, and others, a second method had been shown to be practicable, and this was to use the moon's movements across the sky. It moves fairly rapidly. It moves by its own diameter every hour against the fixed stars. So you can use that as a celestial clock. And if you have tables that tell you that the moon is separated from this star by a certain angular distance, and you have tables that tell you that means it's a certain time, say 10:15 at the place where your tables are calculated for, which might be an observatory such as the one at Greenwich, but could be for anywhere else, then comparing that to your local time from the sun, you can work out your longitude. This was known as the lunar distance method because it relied on that measuring the angular separation between the moon and the sun or another star. And what that needed was a method, which is a set of mathematical calculations, an instrument that could accurately measure that angular separation, and it's quite critical that that's measured very accurately and with some precision. And you need sets of tables that predict what those angular separations will be for your reference place for some time ahead, because obviously if you're going on a voyage, you need tables that work forwards, not retrospectively. And the moon's motion is surprisingly complex. That's the problem. We won't go into the physics of that. That's three-body problem stuff, which is not worth going into right now. So the instruments that were developed were initially the Hadley quadrant or octant was developed with this in mind, but that was improved through the work of Tobias Meyer and others, then English maker John Bird and John Campbell, a naval officer who had tested earlier instruments, and that becomes the marine sextant. Those two work on the same principle. It's just that the sextant can measure slightly larger angles, and it's also a more kind of highly made instrument. So it's interesting that they develop alongside each other. The quadrant more for measuring doing latitude and local time observations, and the sextant for doing these very critical lunar distance measurements. And then the commissioners of longitude start producing these sets of annual tables that give you those predicted angular separations that you can use to calculate your longitude, plus a load of other astronomical data that you need. And they also publish another set of tables to be used alongside them that give you a lot of the data that doesn't change annually. So we have in the 1760s these methods kind of brought to a point where they are known to work, but there's a lot to do because you've got a successful watch. Okay, that's one watch. You've got some sets of tables and some instruments starting to be produced. So you need lots more of everything. You need them to be affordable, and you need people to understand how to use them. So there's actually a lot of work to do at this point to actually have these methods established at sea. And I'm going to talk a bit about kind of different types of navigation, different types of marine activity, and how readily they adopted these methods and why. And I want to start with one of the first sets of activities the Board of Longitude did was to see if these new technologies could be used on the longest distance of voyages. And these were the voyages of James Cook that they initially started to roll out these new technologies and techniques. Now, British explorer James Cook sailed the world 3 times on long voyages of exploration that, as I say, helped test these new methods and importantly showed how they could be applied both for navigation and for the production of better charts through more accurate surveying. On the first voyage, he tested only the lunar distance method with sextants and nautical almanac, became a great fan, said all officers can learn this. He's a very good mathematician, I think. On the second voyage, he also tests the new timekeepers as well as the lunar distance method, particularly this timekeeper, now called K1. It's an exact copy of Harrison's 4th marine timekeeper, the H4 timekeeper. On the second voyage, Cook called it his trusty friend, the Sea Watch. He came to absolutely trust it, that it could work effectively. On the third voyage, and this is an illustration of Resolution and Discovery on the Pacific coast of America from the third voyage, he took again the watch that he'd taken on the second voyage and another slightly simplified watch also by Larkham Kendall. And there's an important point here that these watches are really, really, really complex and really hard and expensive to build. And one of the things Kendall did was try and make simpler watches. And this is an important aspect of the board's work, is encouraging and working with watchmakers Kendall, but also John Arnold, Thomas Earnshaw, who produce new designs, who kind of produce evolutions of Harrison's design of watches that will become cheaper and therefore more available to seamen in navies and in merchant fleets. And what the voyages, the 3 voyages, demonstrate very clearly is that both methods do work, but that support is absolutely needed. Central support is needed to produce these tables annually, but also to work with watchmaking trade to get watches that can be affordable. At this point, the watches are still quite temperamental. So Cook's trusty friend, the watch, stopped working a few months after his death. I'm not sure that that's connected, but and didn't work thereafter. The third of Kendall's watches did carry on working, but hadn't been as trustworthy. So at this point, they're still A, very rare, and B, more temperamental. And I'll talk a little bit more about that because it takes a while for what become chronometers, marine chronometers, to be really trusted as being pretty reliable, certainly if you have enough of them with you. But there's another important point about the Cook voyages, is that they showed that the new methods could be taught to other officers. So I'm coming back to Edward Ryu here, whose complex workings I showed earlier. He was on Cook's third voyage, almost 14, as the voyage set off in 1776, and was a midshipman on the Discovery. Cook was on the Resolution, Ryu was on the Discovery, the accompanying ship. And here we do see him learning and applying the new method. So I've blown it up slightly at the top. So in the red box, we have kind of dead reckoning positions, kind of standard stuff. So course, distance, latitude observed, longitude by account. So that's longitude by dead reckoning. And then in the blue box on the right, we have longitude by timekeeper and longitude by lunar observation and timekeeper. So he is applying these new methods. He's also learning surveying work on the voyage, and this is one of his a plan of Kamchatka, and a lovely sketch of the shore-based temporary observatories that the team set up at various places to do land-based observations. So that tells us that seamen like Ryu were learning the new techniques and learning them seemingly successfully. But again, it doesn't show you what lies behind these figures, particularly the figures in blue. So let's go to some years later in Ryu's life. So what we have on the left are the computations needed to determine longitude by lunar distance. And on the right, computations for local time and for longitude by the watch. So you can see that they actually both have a lot of steps, and this is a mixture of recording observed data, looking up data in tables, and doing calculations, largely additions and subtractions, sometimes using logarithmic tables to allow the navigator to do that. Again, I'm not going to expect you to understand exactly what's going on here, but just appreciate three key things. Firstly, as I said, they require lots of mathematical calculations, whether you're doing lunar distances or longitude by the watch. Although it has to be said, lunars do require more calculations and they also require more observations. And this meant that it was fairly easy to make mistakes. You'll see the calculation on the right is crossed through with a note that this was due to some error reading the sextant. Some pages later on, he accidentally subtracts a correction for the moon's semi-diameter rather than adding it. So again, crosses it out in frustration. So it was quite easy to do little slip-ups and make mistakes. Another key point is that astronomy and mechanical timekeeping don't work separately for any of these methods. So here we have different astronomical observations that are needed. For the lunar distance, you need actually to do 3 different sets of astronomical observations. You need the angular separation of the moon and the star, that's this in this column, but also the altitude of each of the moon and the star. So 3 ideally done at the same time, but perhaps with different instruments. Say altitudes, you could certainly be measuring with an octant. Lunar distance, definitely with a sextant. For local time, you need to be doing sun observations, which are altitudes, so they could be with the octant or the sextant. But you need to be doing astronomy for finding longitude by the watch. And also, you need the watch to do astronomical observations. So for the timekeeping method, these are your watch readings, but you'll see they're timing with a watch, a timekeeper, either a chronometer or a deck watch, which would be compared to the chronometer. So they're not separate and therefore competing in that sense. And it's important to know that the tables, you need lots of different tables supporting this, the Nautical Almanac and other sets of tables. And importantly, you need to be still doing dead reckoning for 2 reasons. One, you need to be able to do observations for either of these methods. If you had a day like it was today in Tallinn, where I don't think we saw the sun all day, you couldn't do your observations for time by the watch. I don't think at any point we've been able to see the moon and any star whatsoever. So you couldn't do any of your observations for longitude by lunar distance. Remembering you'd also still need to be doing your local time observations. So you need dead reckoning as a backup, and you also need dead reckoning to link up different observations. So latitude is measured at noon, but longitude will be measured at other times. So you need to have a fix of a position at a certain time. You need to link those two up in time, which is generally done through dead reckoning. So I've said it's all really difficult. So it seems reasonable to ask, did people really want to do this? Did they want to invest in what are still very expensive things, certainly at the beginning of the period I'm thinking about, through to the mid-19th century? The instrument's slightly less expensive, but you've got annual expense in buying your nautical almanacs. So in short, I'll say it depends who you are, where you're going, and what you're doing. And some of this is going to be actually, quite straightforward. And importantly, the new methods don't replace anything. They just add to and complement existing methods. And a point I'll try to make is that navigators are actually very good at holding lots of different bits of information in their head or on paper, and don't necessarily require all the information to give the same answer. So they're good at making judgments and deciding near enough where they are. And that's an important point. What is good enough depends on who you are and what you're doing. So I'm going to go from essential through to meh. Thinking about 4 contexts. So the first is to come back to people doing surveying and charting. These are people for who the new longitude techniques are essential. I've picked, for some reason, Adam Johann von Krusenstern, who you can learn more about today, but I thought at least he's a local person to think about. Also, he's a good kind of follower, inheritor of Cook's methods in a number of ways, and a great admirer of Cook, very self-consciously an admirer of Cook. Now, he also had come to Britain and served in the Royal Navy in the 1790s, and has certainly become well-versed in navigational practice being carried out in Britain, including the new longitude methods. I don't know what he learned elsewhere. You can correct me if he already knew things from his earlier training in the Russian Navy. But he was certainly a huge fan of British navigational and astronomical instruments. So on his 1803 to 1806 voyage, took a number of instruments by named British makers. So these aren't the actual instruments. These are, however, instruments by makers of whom he had those instruments. So chronometers by Arnold, by Pennington and others, sextants by Troughton, an astronomical quadrant, which is a land-based instrument, by Adams. And he does surveying very much in the same way that Cook does. So the use of temporary observatories on land to help fix points, because land is best. This is another important point. If you're fixing your position, it's much easier to do it on land than at sea. But also the use of instruments for kind of intermediate position fixing with more accuracy than other methods would allow. And there's an important point that going through the Cook voyages and Vancouver and Krusenstern and others, that there is an assumed hierarchy of trust in the methods. It's still a point where chronometers are not absolutely trusted to go reliably. So there's a lot of assurance given by doing astronomical lunar methods for longitude determination as a way of checking that the watches are going adequately. If we skip ahead to the 1830s, however, we come to the second Beagle voyage, which is a worldwide surveying voyage, where chronometers have a much more stable position. Beagle, under Robert Fitzroy, carried 22 chronometers. Compare Cook's third voyage, where they had one timekeeper on each ship. Beagle, one ship, has 22 chronometers. So he has a lot of mechanical clockwork going and trusts that they are reliable much more than someone like Crusenstern or Cook felt able to. And he particularly liked them because he clearly doesn't like astronomy, because he finds it quite difficult to do and time-consuming, and feels that chronometers are certainly adequate to the kinds of surveying they're doing to produce better charts. Although ultimately you do need to kind of fix back to absolutely certain positions, which will be given generally by land-based astronomical methods. But nevertheless, this is a point in the 1830s where chronometers are trusted much more, and certainly a period where the Navy has them on pretty much all ships, the Royal Navy. So that's a very specialist function, which is surveying for the production of charts. And I should say the production of charts is a critical part of this longitude story, because there's huge activity in the 19th century using these new instruments and methods that absolutely is about going around the world producing much better charts, which of course is fundamental to better, safer, quicker navigation. So there is a kind of virtuous circle going on here. But I want to think now about three different contexts for more routine navigation, going in order of preference from most favoured to least bothered for the new techniques. So this is a map of European shipping routes in the period I'm thinking about, mid-18th, mid-19th century. And the high-performance seafarers is what I want to think about. The seafarers going the longest distances into the Indian Ocean. So I'm thinking about, for Britain, the East India Company, but this also applies to, say, the VOC, the Dutch East India Company, and other very long-distance merchant fleets. And what's one of the interesting things about East India Company voyaging is that there are points in the voyage which are really longitude critical. So, typically coming from Britain, they'll come round Africa and into the Indian Ocean. And then there are a number of points which are essentially kind of defined in an east-west kind of a way, where the ships then want to be heading northwards, so either inside Madagascar or turning up to India or to Indonesia and onto China. So these, in a sense, are longitude critical turning points before they then head further on into the Indian Ocean. Now, the East India Company and other long-distance trading companies had long been interested in navigational innovation, and they are absolutely very quick to start adopting both the new longitude methods. The company directors ordered from as early as 1768, just 4 years after successful trials of the new methods, that officers should produce a certificate of competence in longitude by lunar distance, and the ability to work with chronometers is added later. This is a certificate from the 1820s, but to illustrate that point. Over half of East India Company ships were using lunar distances within 5 years of this, so by 1773. By 1792, 80% had chronometers as well. So this is rapid adoption. This is within a generation. In 1792, this is just after company logbooks, including spaces specifically for longitude by chronometer and lunar distance, in addition to, of course, that by account. So we can look into the 1810s, an example of an East Indiaman, the Earl of Balcarras. And you see these are the new logbooks. You'll see longitude, there's dead reckoning longitudes, and then lunar and chronometer there. On this journey, you can see that the ship has a number of chronometers, so here identified by their numbers, as in the number that will appear on the chronometer dial. They're not always doing lunar distance observations, so here they aren't, here they are, and that's also a record of the lunar distance observation. This is becoming quite typical that chronometers, if you've got them, you record it daily if you can, because there might be days where you can't do your local time observations, so it will just say no observation, or just be blank. Lunar distances, by this time, it's becoming much more that you might only do them if you're concerned about the going of the chronometers, or if you're near one of these critical turning points. And as I've said, dead reckoning continues. I'm going to hammer this home. Dead reckoning continues forever, because there are reasons why the other methods might fail, and that's always true. Another point, you may not be able to read this, but on 30th of April, it says, I take a fresh departure at Porto Santo. This is an important point about land. Out of sight of land, you're relying on these techniques. If you see somewhere you know exactly where you are. So that's the point where you might reset things like your dead reckoning positions. So taking a fresh departure means I now have an absolutely certain point that I've seen or been at, and I can reset things. Up to that point, as I said, you might be holding different values for your dead reckoning and your other coordinates, and just holding them together as you would kind of assess if you're in roughly the right place. Right, so that's one context in which there's very rapid adoption, moving to a position where chronometers are doing a lot of the work with lunar distances in a more supporting role. Now think about the Atlantic. It's quite a big bit of ocean, but it's a very, very well sailed route, so people know it quite well. And I'd say the adoption here is more piecemeal. Now, this is an example. I took the Thetis. I took this example because when Krusenstern was in the Navy, he was on this ship on this voyage, going from England to New York. And what I can say about the Thetis is they're doing dead reckoning observations daily and recording it daily, latitude observations as well, but not obviously using other methods. It's quite a familiar route, and it may be that the crew didn't have the equipment or weren't interested in doing it on this voyage, I don't know. But, it's interesting at that point, a ship in the Navy is not regularly using the new longitude techniques, but is also sailing on a pretty familiar route. So Krusenstern may not have seen on this particular voyage those new methods in action. 20 years later, as an example of HMS Elephant, captained by Francis Austen, incidentally the brother of novelist Jane Austen, not otherwise relevant, who's voyaging in areas including the Baltic, but what I'm going to talk about is him in the Atlantic. At this point, he's clearly a big fan of chronometers. He's using them and praising them enormously. This is around 1812, where he's cruising in the Atlantic during the War of 1812 between Britain and America. So big fan of chronometers, does occasional lunars, but not much. Definitely someone who trusts his chronometers. There's a couple of other lovely little nuggets I've found in this particular log. On 14th of December 1812, he signals to an accompanying ship, "Can you lend me a nautical almanac for 1813 for a few days to copy, as we came away without one on board?" So they know the stuff they need. They've just forgotten to bring the right stuff for voyaging into the next year. So they need the next edition of the nautical almanac. On the last day of the year, he reports that the ship accompanying them, the Hermes, had encountered a brig bound for Lisbon from New York, apparently with a license, so legally crossing from America. It had sighted a squadron of ships 6 days previously, but as it had kept no reckoning of its position, it couldn't give latitude and longitude for where it had seen those ships. So this is interesting, someone who doesn't appear to be doing any navigation, just relying on the fact they know where they're going and they'll get there. I don't know if they were being a little coy about what they knew about the position of the squadron they'd seen, but it was an interesting detail about the extent to which people are bothered about doing very detailed navigational technique in sea areas that they feel very comfortable with. Now, in the Royal Navy, within a couple of decades of Austin on the Elephant, the Navy has adopted chronometers for all ships, and certainly by mid-century, it's a standard piece of equipment. Although that doesn't mean they're always using them every day. I'll mention that a little later. Just in passing, there are, thinking about merchant vessels, the Hudson's Bay Company, who are going from Britain to Newfoundland regularly, very slow to adopt. Unlike the East India Company adopt very quickly, Hudson's Bay, on a very familiar route, they're obviously happy with, really don't start adopting new methods and practices until the 1820s. So this is kind of 50 years or so after the introduction in principle of these new methods that they start, thinking about adopting what presumably by then are more affordable practices. The last area I thought it'd be interesting to think about is the Baltic. Now, this is a very small sea area, and it's hard to spend long out of sight of land. So it might not surprise you to know that actually it doesn't really matter too much about doing these new techniques. So here I have the Active in 1796, voyaging between London and Riga and back. So again, it's doing dead reckoning observations, sometimes notes when no observations are possible. And that seems to remain actually quite typical for ships in the Baltic area. I've looked even at a couple of steamships in the 1850s, naval vessels coming into the Baltic. They have a chronometer, and they have logbooks with entries for chronometer longitudes, but are barely bothering to record their position in an area like this. So it's, the point being that this is kind of a sea area where it actually doesn't matter that much. You kind of know where you are, and if you sail a bit, you'll find somewhere you're familiar with. I want to come towards a conclusion by thinking about one shipwreck, just to show that although there are new methods, it doesn't mean shipwrecks don't happen. And partly because this illustrates some things about the issues still inherent in navigational practice. So the Thetis sank on 4th of December 1830 after crashing into rocks on Cabo Frio, north of Rio de Janeiro. 25 sailors died. And it was a much discussed wreck, certainly in Britain. There was a lot of surprise. This was a very well-known, well-charted sea area, very well travelled, and they seemed to have run at high speed straight into Cabo Frio. Robert Fitzroy writes about it in his account of the Beagle voyage. He has a little aside about this accident. Surprised that after a run of just 19 hours, so a very short run, they managed to get their position so disastrously wrong, although he says that sun, moon and stars had not been visible. So that could be a contributing factor. The court-martial that happened blamed the captain and the master for relying only on dead reckoning and for failing to take soundings. So failure in basic navigational practices and for making insufficient allowance for the effect of strong southerly winds on sea currents. So we're back to the issue of sea currents still being very evident. The captain and master for their side blamed it entirely on unexpected and extraordinary sea currents. And coincidentally, I remember years ago someone telling me that for P&O ships in the 19th century and beyond, this idea of an extraordinary and unexpected current is often the thing cited in wrecks, something that's very hard to prove or disprove. However, other explanations for the wreck did later emerge, notably the possibility that the magnetic compasses had been somehow disturbed by local magnetic effects. So some of the basics of navigation, even in the 1830s, are still very much kind of in doubt and potentially problematic. So just tying things together, I kind of showed you some of the instruments and aids that navigators had in the middle of the 18th century. Thinking about the middle of the 19th century, a lot of them look very, very familiar. We still have the leaden line, we have magnetic compasses, we still have the login line for speed, although new innovations like mechanical devices for measuring ship speeds had been introduced from the early part of the century, although the kind of traditional throw a bit of wood over the back of the boat with a rope tied to it were still very common. This is a sketch from just after mid-century. Magnetic compasses were also the subject of a lot of intensive research from the late 1830s, and this becoming increasingly problematic with the increasing use of iron and steel for ships. And also bearing in mind that with the introduction of new propulsion techniques, actually accurate and rapid reading are both very important. But we do have the new methods, sextants, chronometers, and better charts. And we have our old friend, the good looker out. Absolutely critical, never goes away. I should have said asking a friend is also still here as well. But this I put an example of one of these 1850s steam vessel logs where you see they do have DR and chronometer lines for longitude, but not for lunar observation. So lunars have certainly dropped back to a much more supplementary role at this point. And I would say two things also. So dead reckoning hasn't gone away, and it won't go away, and it shouldn't go away, though the new longitude methods have come in. Land is still always best. If you sight a bit of land, you know where you are, and that's still the best way. And here, they're still recording their position. Another way of recording position is in terms of your bearing and distance from a known point of land, as well as recording it in terms of dead reckoning values for latitude and longitude and observed values where you have them for latitude and longitude. So that is all I have to say. I'm just going to put that up because I love that image. I guess my point is that by the mid-century, navigation, which was a very, very mathematical art, is still incredibly mathematical. It's even more instrumental than it has been, in the sense of using instruments and a greater range of instruments. But a lot of it has actually remained the same, and kind of the types of navigating, the kinds of seafaring you do, very much affect which of those methods you have adopted and to what extent. So thank you very much.
Thank you, Richard. Fascinating, and I'm wondering, when did it get easier?
When did it get easier? Well, that's a good question. I mean, I guess you could say that things like the introduction of radio signals for checking chronometers in the early 20th century is one of the things. New techniques of navigation which brings chronometers together in different ways, so position line navigation actually from the mid-19th century, and that's something I haven't looked at, is how that gets adopted, which would be very interesting. And then really the big revolution is from the mid-20th century with the introduction of electronic navigating systems, so things like Decca and Loran, but then obviously from the 80s, satellite navigation, which kind of wipes out a lot of practice, perhaps dangerously, because actually you should still be doing your dead reckoning. I'm just saying. GPS, whatever satellite nav system you're using, can go wrong. So you need another method going on alongside it. Yeah.
Do we have any questions from the audience? Simon, please.
Yeah, so thanks very much, Richard. I just have a question. So when you have a logbook where it has the three different measures, dead reckoning, lunar method and chronometer, do you have any sense of how they then made decisions about what they actually were based on the three? Like which one to go with, if you like?
I mean, often it sort of doesn't matter, because being really precise about where you are matters where you might hit something or where you might be going the wrong way. But so in terms of kind of danger, I think it's fine. I think it's fine to hold them. I think they're different navigators will have different assumptions about which ones feel better. I think there's a lot of kind of gut feeling going on. But I don't think we ever see any real attempt to kind of resolve one or, use one to correct another, except, maybe using lunar observations to think about the chronometer performance is a thing. But yeah, it's very much kind of holding potentially quite differing information together. And then lo and behold, you see a bit of land you recognise. Perfect. You can just reset everything. And then you can go, okay, I think this now tells us what the chronometers are doing. I mean, I didn't go into rate, but, with chronometers, so I'll talk briefly about rate now. Okay, so rate is, ideally your chronometer would move 24 hours over 24 hours, but it might actually, rather than reading midday on one day and midday 12:05 the next day at the same time, as it were, that's okay, as long as if it does that every day, it's a really, really good timekeeper, because it just means every day it instead of showing 24 hours, it shows 24 hours and 5 minutes. If it does that day in, day out, you can just do a simple arithmetic correction every day. The problem is that the rate, and that's the variation between what it should be saying and what it does say, doesn't stay the same. Or if it does, hooray. And that's where things like lunar observation or going to a point of land with a known position and checking from land observations how your chronometer's doing would allow you to tell that. if its rate has varied, then you get into all sorts of questions about how do you sometimes retrospectively kind of compensate for the rate. Do you assume the rate has changed linearly between those 2 points, or actually do you assume it does some curvy change? That's not answering your question. It's just a sort of thing I hadn't mentioned that is of interest and a further complication of chronometers, and actually a reason to not trust your chronometers might be the rate keeps changing. This makes it really difficult to work out what the true reading is. Yeah.
Anyone?
Did I get it correctly that for the dead reckoning method, you need to measure for every hour of your whole voyage?
Yes, ideally. Royal Navy protocol was hourly, log and line, as long as you can do it. You can do it. The good thing about dead reckoning, you can do it in most conditions, and obviously visibility doesn't matter. If you're in the middle of a storm, you obviously can't do it. But yeah, so protocol in the Navy was hourly recording of the log, the speed given by the log and the ship heading. Some merchant vessels seem to have done speed every 2 hours.
And so were there specific sailors charged specifically with that task? And you mentioned the storm. What happens when there is a storm? Is there any way to get back on course?
Yeah, it depends when we're talking. If you're just doing dead reckoning, you just have to go, I think the storm drove us, this far and this heading. You can still, as long as you can see a compass and it's not doing that too much, you can still keep some kind of record. So yes, officers are doing the recording of data, but as you'll have seen in this one, it's kind of, you've got a couple of ordinary seamen doing the actual hard work and, an officer watching and doing the recording. So ship logs are kept by each of the officers. I'm talking about the Navy here. Midshipmen, lieutenants, the master, the captain are all keeping logs, and these are official things, which is why they look quite neat and hide all the sums and the errors. But yeah, it's kind of seamen and sounding. That's going to be done by an ordinary seaman, not by an officer. The officer will just record the data. Yeah.
Let's take one more. 2, 3 more, 4 more, 5.
You can accost me over a glass of wine.
Let's see. Okay, let's just go with it, please.
Okay, thanks. Thank you for a lovely talk. I was fascinated about the human-made error in one of the logs, which had been crossed out. Have you also seen somewhere that people would write when an instrument was making an error?
Yes. Yeah, absolutely. It'll be chronometers going wrong, or the one crossed out there, was his use of the instrument. That is true. But occasionally it's luck. You'll suddenly come across something, and notes of different observers. If you look at the Cook voyages, there are kind of notes about the different observers who'd been doing thing. And I know King on the third voyage kind of writes about different officers producing different results, shall we say. But his thing is they just need to do more practice and learn it properly. It's not a fundamental problem with the technique, it's just a problem of their learning. It does come up. I love to see things go wrong because it's a great way of learning. But it's very much kind of, if you come across stuff, let me know. But yes, absolutely. And sometimes, I'll just say sometimes, like on the Elephant, I was saying where Austin, he certainly records where he thinks actually the chronometer's going really well. And Cook does the same kind of way. He says, coming on the third voyage, and they get to Tenerife and they do some land observations, and he makes a comment that it seems like the chronometers have been going just brilliantly up to this point by comparing their values with observations done at Tenerife. and also with lunar observations done on the ship at anchor while they're there.
We have one over there.
Thank you. I would like to ask about how deeply did the navigator have to understand astronomy, or could he just rely on these formulas, or is there a change in this after mid-century?
Yeah, a lot. Generally, it's kind of codified, so you just have to follow the steps, and you do actually. And I could have produced. There were produced from the late 1760s forms, thinking about longitude, say lunar distance determinations. That you would get forms which would say, you fill in here your lunar distance, your altitudes. You should have many of them. You do your average, and then it says, look up table 9 in the Nautical Almanac and get this thing, etc. So it takes you through the steps. And I think certainly for dead reckoning, where you're trying to resolve different courses into changes of position, north, south, and east, west. Again, it's looking up data in tables. So the maths you're doing is pretty much addition and subtraction. So it's just about being rigorous and careful with that, rather than understanding the astronomy. There are people who can do the harder stuff. For example, on I think both the first voyage and the third voyage, Cook voyages, they didn't have nautical almanacs for every one of the years. So in the final years of each of those voyages, they were going back to other sets of tables to do more fundamental maths to work out the problems. So they didn't have the kind of ready reckoning that the nautical almanac gives you. So in short, no, they didn't have to understand spherical trigonometry in detail, but they did have to be kind of confident in basic mathematical operation.
Thank you.
There was one more method for the longitude determination using the occultations of Jupiter satellites.
Yes.
How much was that considered in comparison of lunar and chronometer meters?
Yeah. So yes, you can use, because Jupiter, from 1610-ish, Jupiter was known to have a number of satellites going around it. Initially four discovered, and it's Galileo who discovered this and realised that this could be a way, this is another celestial clock, because these are very predictable and they're quite regular, so you can have tables of these disappearances and reappearances of each of the four most visible moons of Jupiter. And the Nautical Almanac included tables of those predicted appearances and disappearances. However, so it's brilliant on land and is used on land from the 17th century very successfully, and there are other tables produced in the 17th century. And it's tried at sea an awful lot. Galileo comes up with some devices like an observing helmet for use on a ship, which doesn't really work. At the same time as lunar distances, and Harrison's timekeeper are trialled in the 1760s, there's actually an observing chair for observing Jupiter's satellites is tested at the same time, turns out to be completely useless. The problem is that it's a very small target and it's very far away. So you need quite a strong telescope to see it, and so your field of view is tiny. So it's really hard to keep it in view, and actually it proves to be impossible on a ship. So it's understood to be a really good method and is useful on land, but it's never, in this period, never perfected at sea at all. You could do it now because you can, you've got the kind of technology of digital kind of camera, digital optics that could allow you to do that at sea. But it never makes it to sea, and it's something that is tried right through. So the Board of Longitude gets wound up in 1828, and they are receiving schemes for Jupiter's satellites observations right through to their demise in 1828. So everyone knows it could work and could be really good, but it's just never practical at sea in this period. Yeah, thank you.
I think we had one more in the back, and then let's wrap it up, I think. Just food.
Thank you. Sorry for prolonging this.
That's
Small question. The comparison of the different methods that you showed were really fascinating. I was wondering if you'd seen and how it was available on those documents, how they accounted for drift, how they understood it, because that wasn't something that would show up in instruments.
Yeah, not on that. And I don't yet have many good examples that really show that greatly. Well, there's two things you need to account for. One is leeway, which is the difference between basically the way your ship's pointing and the way it's actually moving through the water. And that's often determined by looking at the wake, compared to the ship, the centre line of the ship, but also the effect of currents. So yeah, it depends what you mean by, because each of those is in a sense a form of drift, isn't it? So leeway. So people make account certainly for leeway. I think some of that is kind of finger in the air. Someone may correct me, Carol. You may know better. But some of it is a little bit of guesswork and knowing your ship. Currents are almost impossible to measure, and I mean it's interesting. Again, coming back to the Cook voyages, one of the things I think both Cook and William Wales, astronomer on the second voyage, thought would be possible would be to use accurate longitude determinations to measure currents, because particularly if you do it over quite a long run, and you could see if you trust your longitude, basically Cook says if you're doing really good dead reckoning and you have really good longitude determinations from timekeepers, then the difference between the two is the effect of the current. Assuming there are no other errors, which is big assumption. But yeah, it's a huge problem, basically, because you're moving with the water. So how do you measure a current? Is not straightforward. And there were attempts to do that. Again, this is all about throwing things over, but you sort of throw something over which is then kind of has a sea anchor, and then you can see how that's you and it are moving relative to each other. But it's not straightforward at all. So there's a lot of hope that these new methods will actually aid in that, but that doesn't kind of work out that way. But yeah, thank you.
Okay, thank you, Richard. I think perfect introductions.
Thank you very much. Thank you.